In this video, I will be arguing that decimal is better than dozenal. There are many videos on YouTube arguing that dozenal is the best base, and honestly, I don't get it. They only really talk about fractions, but there's a lot more to what makes a base good than that. Mainly size, neighbors, and divisibility tests. Chapter 1. Dozenal fractions aren't that impressive. Dozenal's main gimmick is that it's divisible by 2, 3, and 4. This is good because it means that 1/2 is 0.6, 1/3 is 0.4, and 1/4 is 0.3. Decimal and dozenal are tied on how they handle 1/2, but dozenal is objectively better with thirds and fourths. But here's the thing, no one ever talks about fifths. In decimal, a fifth is 0.2, very simple. In dozenal, it's 0.2497 repeating. Yikes, that's awful. 1/7 is 0.1861035 repeating. Both of these are awful. In fairness, decimal sucks at sevenths too. 1/7 in decimal is 0.142857 repeating. But as decimal is smaller, it's ever so slightly easier to remember since each digit only has 10 possible states as opposed to 12. So I consider that a win for decimal. Chapter 2. Decimal's fractions aren't that bad. Let's look back at decimal. It handles 1/3 as 0.3 repeating. Not great, but it's a single digit to remember and it's pretty easy to derive on your own. Also, 0.25 terminates, so it's really not that bad. Dozenal's quarter is a gimmick. Dozenal makes quarters slightly better and thirds a lot better, but at the cost of fifths. Dozenal handles sixths really well, but decimal isn't awful at them either, just being 0.16 repeating. Not great, but it's easy to find as it's just half of 1/3. Chapter 3. Dozenal's quarter is a gimmick. Let's talk about prime factorizations. The prime factorization of a number is all of the primes that when multiplied together create that number. For example, 10's prime factorization is 2 times 5, which makes it a pretty meh choice for a base. Not great, not terrible. Dozenal's prime factorization is 2 times 2 times 3. Repeats are not necessary and add bloat to a base. This is because the powers of a base will repeat those primes for you. 10 squared is 2 times 2 times 5 times 5, so 1/4 can be represented with 2 digits terminating. Chapter 4. 12 is a big number. Dozenal is a larger base than decimal, meaning its math is slightly more complicated and it's slightly less informationally efficient. No one cares about informational efficiency since it doesn't seem to actually exist, but it's still worth bringing up. Some people actually prefer larger bases over smaller ones, but I do not. The smaller a base is, the better, as things get simpler and fractions typically get better. Chapter 5. Divisibility tests. There are 5 divisibility tests in decimal that are easy enough to use. By 2, 3, 5, 9, and 11. Why not 10? Well, I'm not including divisibility tests that can be derived from other divisibility tests. Like you can tell if a number is divisible by 10 if it's divisible by 2 and 5, and if a number is divisible by 2 and 3, it's divisible by 6. Wait, then why did I include 9? Well, you can't check if something is divisible by the same number twice, so it's not actually derived from 3. You'd have to divide the number by 3 to check again, and that's not how we check for divisibility by 9 in decimal. The easiest tests are the last digit tests. If the last digit is 0 or 5, it's divisible by 5. If it's 0, 2, 4, 6, or 8, it's divisible by 2. If you add up all the digits, you can test if it's divisible by 3 or if it's divisible by 3 times 3, 9. Lastly, you can add up the alternating digits, every even indexed digit and every odd indexed digit. When you get those two numbers, subtract the evens by the odds, and if that number is divisible by 11, it's divisible by 11. Let's look at dozenal. There are 5 divisibility tests that are usable, by 2, 3, 4, 11, and 13. Remember, I'm not including 6 because it's just the divisibility test for 2 and the divisibility test for 3, but I am including 4, since 4 is 2 times 2. It's not quite if the number is prime that it gets to stay, it's a bit more complicated than that. The easiest are 2, 3, and 4. If a dozenal number ends in an even number, it's even. If it ends in a multiple of 3, it's divisible by 3. If it ends in 0, 4, or 8, it's divisible by 4. These are pretty good, but it lacks 5, which isn't great. Sure, 5 isn't that useful, but it's one of the smallest primes. And instead it favors 11 and 13? Yuck. You can test divisibility by 11 by adding up the digits and checking if that number is divisible by 11, like 9's in decimal, And then you can check 13s like you do 11s in decimal with the alternating sum thing. Lastly, you can check divisibility by 4 in decimal. It's just a little bit harder. If the last digits of a decimal number are a multiple of 4, the whole number is. Alternatively, you can divide the last two digits by 2 and check if that number is even. So again, absolutely no divisibility test by 5 in exchange for a better 3 and 4 divisibility test. I know, 5s aren't that important, but there's still a small prime that can't be crappily accommodated for like composites can, like decimal with 4s. Dozenal and decimal have the same number of easy divisibility tests, but decimal favors better primes than dozenal does, and dozenal wastes its time with composites and large primes. Chapter 6. Finger counting. There's a very common method for finger counting in dozenal, and I don't like it that much. Basically, each hand is a dozenal digit, and your thumb points to the 12 segments of your fingers. I don't like it for two reasons. Numbers don't look distinct, especially from a distance, and it's hard to remember the order they go in. Decimal standard isn't great either, but there's this cool method called Chisenbot. Basically, your fingers are each worth 1 and your thumb is worth 5. So you count from index to pinky, then extend your thumb and retract the rest of your fingers, go back up, and once all fingers are extended, you switch to the other hand where the 4 fingers are worth 10 and the thumb is worth 50. This gets you all the way up to 99. Chapter 7. Sexamal. All of this has led me to 3 main realizations. Repeats of primes in the prime factorization are bad, smaller bases are better, and neighbors matter. Let's look at 12's factorization again. 2 times 2 times 3. What if you remove that repeat? Well, that leaves us with 2 times 3, or 6. 6 is adjacent to 5 and 7, which are the next two primes. This makes sexamal an amazing base, way better than both decimal and dozenal. It's the most obvious choice when you start thinking about what makes a base good, and that's why I started this video with, I'm not sure why dozenal is so popular. Because if you try to find the best base, everything points towards sexamal. Sexamal is the most obvious choice. Chapter 8. Conclusion. Decimal is great at 2s and 5s, and okay with 3s, 4s, 6s, 9s, and 11s. Dozenal is great at 2s, 3s, 4s, and 6s, okay with 11s and 13s, but absolutely terrible with 5s. It doesn't even half support them like decimal supports 4s. I'll admit, 12 being a superior highly composite number does indeed make it look tempting, but it's a bit shallow, and 12 has bad neighbors. You can still check divisibility by 6 in decimal by checking if it's divisible by 3 and even, so it's really not that bad. Sure, it's not a last digit divisibility test, but it's workable. Dozenal works very precisely with 2, 3, and 4, but fumbles everything else. Decimal works okay with most primes below 7 and 11, and weirdly prioritizes 5s. Both of these are bad bases. I'm not advocating for decimal at all. I'm just saying that I think decimal is ever so slightly better than dozenal, and I don't get why all those really old YouTube videos advocate for dozenal as opposed to sexamal.